Hello, I am Seema and welcome to part 9 of the chapter Chemical Kinetics. In part 8, we were discussing the integrated rate equation for first order reactions. And in that we studied that if you have to calculate the rate constant in terms of log to the base 10, rate constant was equal to 2.303 upon T2 minus T1, where you are calculating the concentrations of the reactant at time T2, the concentration would be R2, and at time T1, the concentration would be R1. So T2 minus T1 would be delta T, that is the change in time, log R1 upon R2, where R1 and R2 are the molar concentrations of the reactant at time T1 and T2. You had understood. In case you do not understand what I am telling you right now, I would encourage you to watch the previous video and you would understand the how we calculated the rate constant for a first order reaction. Now, if you remember, when we were studying chemical equilibrium, whenever we had gaseous reactants and products, calculating the concentration of gaseous reactants and products is difficult. But calculation or measurement of their partial pressures is easier. And therefore, whenever you have gaseous reactants and gaseous products, it is comfortable to use the partial pressure instead. So the equation has to be modified in terms of the partial pressures. Let us understand how we do it in the case of a gaseous reaction for the equilibrium, not the equilibrium constant, for the integrated rate equation or the rate constant. Now this is a first order reaction where you have A giving you B and C. The products are B and C. At time T is equal to 0, the pressure of the reactant is Pi, that is initial pressure, Pi atmosphere. And initially the reaction has not started, therefore the partial pressures of B and C products are 0. Now at time T, the pressure, let us say that X, due to the reaction of the or the using up of the reactant, X amount of partial pressure of the reactant decreased. So the pressure decreases and X amount decreased. So Pi minus X atmosphere would be the partial pressure of the reactant at time T. And according to the molar concentrations, we know equimolar substances would have the same amount of pressure also. So if you had 1 mole of A decomposing, it gives you 1 mole of B and 1 mole of C. Then if 1 atmosphere of A was decreased, then 1 atmosphere of B and 1 atmosphere pressure of C would be formed, because the pressure of the gases is directly proportional to the molar concentration. So if X atmosphere decreased, it means that X atmosphere of B was formed and X atmosphere pressure would be the pressure given by C. So at time T, what would the total pressure be? The total pressure would be the partial pressure of A plus partial pressure of B plus partial pressure of C. But in the rate equation, we know that for calculation of rate constant, you need the partial pressures of A at time 0 and at time T. That is, time 0 is T1 and time T is T2. So you must know the value of the partial pressure of A at both the times to use it in the rate constant, to calculate the rate constant. But before that, let us just see numerically how will we do this. The total pressure is the sum of PA, PB and PC, partial pressures at time T. This total pressure, if we talk in terms of this, PA, what is PA? PA is Pi minus X. The initial, whatever the initial partial pressure was, minus X. That is the partial pressure of A at time T. So it is Pi minus X, and the partial pressures of B and C at time T are X and X. So we substitute that. We write Pi minus X for PA, for PB we write X, and for PC also we write X. So this becomes the total pressure. So Pi minus X plus X minus X plus X get cancelled. You get Pi plus X is the total pressure at time T. Why do we do this? We do it because we want to calculate, we want to find out in terms of these Pi and PT, the partial pressures, the value of X. What would X be equal to? So from this equation, that is P total is equal to Pi plus X, we can calculate X. So what is X? X will be equal to PT minus PI. That is P total at time t minus the initial partial pressure of A. So PT minus PI is the value of X. Now we can substitute this value of X in this equation. PA we can substitute X to calculate the value of PA. Why do we want to find out PA? Because to calculate the rate constant we must have PI and PA. So to calculate PA from this, let us substitute the value of X in it. So PA becomes equal to PI minus X. And if we substitute the value of X, which is PT minus PI, we get PI minus PT plus PI. If we do not put the bracket, it will be minus PT minus PI. So if you remove the bracket, you'll get PI minus PT plus PI, which means you'll get 2PI minus PT. That is the value of PA, that is the partial pressure of A at time t. Now in the rate equation, the integrated rate equation, rate constant is equal to 2.303 upon T, where T is actually T2 minus T1. In this case, T2 is T and T1 is 0. Therefore, we've written only T. Right? In case it was not initial and they were two different stages and they had pressures at different times, then you would have had to use those different times. So T, whatever the value of T, you could call it delta T, 2.303 upon T into log PI upon PA, where PI is the partial pressure at time 0 and PA is the partial pressure of the reactant at time T. So when you simplify this, or rather substitute the value of PA, which is this, you get 2.303 upon T log PI upon 2PI minus T. You've just substituted the value of PA here. So this is the equation that you get in the integrated rate equation for a first order reaction where you have gaseous reactants and products, and how would you modify it in terms of partial pressures. Now, there are two numerical problems which are based on the calculation of the rate constant or based on this topic, which we will be solving. This first question is the solved example of your textbook. It is example 4.5. The question reads that the initial concentration of N2O5 in the following first order reaction, N2O5 gives you twice NO2 plus half O2, was 1.24 into 10 to the power minus 2 capital M, which means moles per liter, at 318 Kelvin. The concentration of N2O5 after 60 minutes was 0.20 into 10 to the power minus 2 moles per liter or molarity. You have to calculate the rate constant of the reaction at 318 Kelvin. 318 Kelvin is that temperature, so the temperature is constant. And the molar concentrations of the reactant at two different times. And what is the difference between the two times? It is 60 minutes apart. So delta T or T is 60 minutes. And here we are talking of concentrations, moles per liter. It means we'll be using the same equation, only here we'll be using R1 and R2 as we did in video 8. So give me a moment, let me start writing this. So let us first write down what all do we have. We have been given initial concentration, that is R1, and R1 is 1.24 into 10 to the power minus 2 moles per liter, molarity. And the concentration of the time is T is equal to 60 minutes, and R2 is given to us, which is 0.20 into 10 to the power minus 2 mole per liter, right? So you have to calculate, the concentration is given, you have to calculate the rate constant. You are expected to calculate K. So K would be equal to 2.303 upon T log of this R1 upon, the 1 should be outside, upon R2, which would be equal to 2.303 upon T is 60 seconds, 60 minutes, right? Log concentration R1 is 1.24. I was just checking if the video has gone off. So it is 1.24 into 10 to the power minus 2 moles per liter upon 0.20 into 10 to the power minus 2 moles per liter. So the moles per liter and moles per liter get cancelled, and when you calculate this, you get 2.303 upon 60 minutes log, and the value of this when you solve this is 6.2. 6.2. And when you solve this, all of this, you'll get 2.303 upon 60 into whatever the value of log 6.2 is, find out, and then calculate this. You will get the answer that would be 0.0304. 0.0304, and there is only one unit here, that is minutes, and that's in the denominator. So your answer will be 0.0304 minute inverse. Right? So this is example 4.5. And now I'll do example 4.6. Give me a moment to write it down. Now this is solved example 4.6. Let me read the question. The following data were obtained during the first order thermal decomposition of N2O5 gaseous at constant volume. The volume was constant, and although it is not really significant here, when you say the volume is constant, it means it's in an enclosed vessel. Therefore, the partial pressures, the total pressure would be the sum of the partial pressures in the enclosed vessel. So that way it could only be a hint that you have to use the partial pressures here. And if you look at the reaction also, the reactants and the products are gaseous. And in the question, what you've been given is also the pressure. So we have to solve this question in terms of the partial pressures. Anyway, let me continue reading the question. So it was during the first order thermal decomposition of N2O5 at constant volume. The equation is twice N2O5 gaseous gives you twice N2O4 gaseous plus oxygen gaseous. A table is given where you have the serial numbers, the first and second. There are two readings at time t, where t is equal to 0 and t is equal to 100. The total pressure, now the partial pressure is not given, the total pressure is given at time 0 and at time 100. So that is T1 and T2. So 0.5 and 0.512. You have to calculate the rate constant. We know what is the equation for rate constant that we just solved. Rate constant, if it is a gaseous reaction, is 2.303 upon T log Pi upon Pa, where Pi is the initial partial pressure of the reactant and Pa is the partial pressure of the reactant at any time t. And t is actually delta t, the difference between the time t2 and t1. Now, having understood this, let us first see what does the equation give us and how do we solve this. We first write down the equation. Twice N2O5 gaseous gives you twice N2O4 gaseous plus oxygen, which is also gaseous. Now the initial, at time t is equal to 0, that is initially t is equal to 0, the concentration, the pressure, the partial pressure is 0, but the total pressure is 0.5. But initially you only have N2O5, right? Initially you only have N2O5 and 0.5 is the partial pressure of N2O5 initially. 0.5 atmospheres, it is in atmospheres. And initially the partial pressures of both N2O4 and oxygen would be 0. But at time t is equal to 100 or T2, at t is equal to 100, the total pressure, what would you say, what would happen to N2O5? Some of N2O5 will be used. So 0.5 and whatever, since there is 0.5 is the total amount. Now if 2 moles of N2O5 are used, you get 2 moles of N2O4 and 1 mole of oxygen. So the molar proportion and the proportion in partial pressures would remain the same. So let us say that out of 1 mole, X moles dissociates. Then out of 2 moles of N2O5, let us, it would be 2X, And if the decrease in partial pressure also in terms of x we write, it would be 0.5 minus 2x. Because this is 2 moles. We have to write the stoichiometric coefficient. You have to keep in mind, because if 1 mole, out of 1 mole, the partial pressure that decreases is x, then out of 2 moles, the total pressure that was out of 2 moles, it would be twice x. Then N2O4, in terms of the partial pressure that increases of N2O4, again the stoichiometric coefficient is 2, therefore you write 2x here. That would be the partial pressure of N2O4. And oxygen has only 1 mole, therefore this would be x. So the total pressure at time t is equal to 100 would be 0.5 minus 2x plus this. Now I'm just following the same steps as we did when I explained the equation to you. How do we write it in terms of partial pressures? So let us write, what would PT be? PT, that is P total, would be the partial pressure of, if I write this as N2, okay, this would be, if this is A, this is B, and this is C. So partial pressure of A plus partial pressure of B plus partial pressure of C. You could alternatively also write these as the formulae, that is the partial pressure of N2O5, partial pressure of N2O4, and partial pressure of O2. Anyway, the total pressure would be this at time t, which is equal to 100, which is equal to, what is PA according to this? 0.5 minus 2x plus 2x plus x. This will be the total pressure. What is the aim? The aim here is we must find out x in terms of PT and PI, and that is what we want to do. So minus 2x and plus 2x goes off, you'll get 0.5 plus x is PT. Right? So what is x? X would therefore be equal to PT minus 0.5. Whatever is the total pressure, minus 0.5 will give you the value of x. Now, in order to substitute this value, use this in this equation, we need to find out the value of PA, right? And the value of PA at time t, that is the partial pressure of N2O5 at time t, and we've been given the total pressure. But using this, let us say what is the partial pressure of N2O5? The partial pressure PA at time t is equal to 0.5 minus 2x. And the value of x we already know. So according to this, what would PA be equal to? Let us substitute the value of x here. It would be equal to 0.5 minus 2 into PT minus 0.5. That is twice PT, partial pressure at time t, this should be a subscript, minus 0.5. So this would be equal to, if you take this, solve this part, 2 minus 2 into minus 0.5 would be 1.5 plus 1.5, and 2 minus 2 PT. Again, it should be a subscript. I'm making this mistake. It should be a subscript. PT, partial pressure at time t, right? Now this is the value of PA. And what is P total that we have? Time t that we are given is equal to 100 seconds. 100 minus 0 is 100 seconds. And PT is given to us, which is equal to 0.512 atmospheres. So if you substitute the value of PT here, you can get the value of PA, right? You can get the value of PA would be equal to 1.5 minus 2 into 0.512 atmospheres, right? And this, when you calculate it, would be equal to 0.476. This would be equal to 0.476 atmosphere. This is the partial pressure of the reactant at time t. Now we have all the values. We have PA, we have PI. PI is this, PA would be this value, and 2.303 T given to us is 100, and we can now substitute all the values in this equation. So from this we'll calculate K. K would be equal to 2.303 upon 100 log of Pi is 0.5 upon 0.476. And when you solve all of this, you will get 2.303 upon 100 into 0.0216 into 0.0216 is the log of all this. 2.303 upon 100, just one more step that I am writing down from as it is given in the book. Although when you solve it, of course, you would first find out the log of this. You'll solve this, then find out the log of that value, which is this much, and then multiply it. And the answer that you get is 4.98 into 10 to the power minus 4. 4.98 into 10 to the power minus 4. And what about the unit? Here you have seconds. And here both you have atmosphere, they'll get cancelled. So second in the denominator, so the unit that you'll have would be second inverse. Right? So this was the value of the rate constant. So I hope with this you understand how to calculate the integrated rate equation for both zero order and first order reactions. And with this, I wind up this video. I hope you found it helpful. And if you did, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.